Om Swastiastu. Hello everyone. My name is Samuel Benaya Batubara with student number 220553197, and in this video I will explain about metal forging process and equipment from the book Manufacturing Engineering and Technology 6th edition chapter 14. Forging is one of the earliest metal working processes, dating back thousands of years. It used compressive force to shape metal, and it's widely used today to produce high-strength components such as gear and turbine shaft. Forged parts have excellent mechanical properties due to controlled metal flow. This slide compares forging with casting and machining. Forging produces superior strength because the metal flow and grain structure are controlled. Unlike machining, it utilizes material more efficiently, and in some precision forging operations, almost no machining is required. Forging may be carried out of a cold, warm, or hot. Cold forging provides excellent accuracy but requires higher forces. Hot forging is more common because it reduces resistance during deformation, although surface finish is not as good. Open die forging is the simplest process where the workpiece is compressed between flat dies. As the height decreases, the metal flow outward. This process is widely used for large components such as shafts and rings. Because of friction or thermal difference, the workpiece develops a barrel shape during open die forging. Another related operation is cogging, where deformation is applied in a series of bites to control shape and reduce thickness gradually. In impression die forging, metal is shaped inside contoured dies. As the dies close, some material flows outward to form flash. The high friction in the flash forces the remaining material to fully fill the die cavity. This slide shows the forging force equation. Open die forging force depends on friction and workpiece geometry. Impression die forging uses a multiplying factor K, which increases with part complexity and flash formation. Closed die or flashless forging eliminates flash, requiring very accurate blank volumes. Precision forging is increasingly used to produce near-net shaped components with the fine details and high dimensional accuracy. In addition to basic forging methods, several specialized operations exist to produce specific shapes or surface features. These include coining, heading, piercing, hubbing, orbital forging, and swagging. Coining is a high-pressure closed die process used to reproduce very fine details, such as on coins. Pressure can be several times the strength of the material, producing excellent surface finish. Heading is an upsetting process performed on the end of rods of wire to form bolt heads or rivets. It must be carefully controlled to avoid buckling when the unsupported length is too long. Piercing is used to form cavities or recesses, while hubbing presses a hardened punch into the die material to form shallow die cavities. Both are essential in producing detailed shapes. Swagging uses rapidly reciprocating dies to reduce diameter or form internal profiles. When a mandrel is used, complex internal geometries such as riffling can be produced. Forgeability refers to the material's ability to deform without cracking. Tests such as the upsetting and hot twist test determine the forging temperature range. Aluminum alloys have high forgeability, while superalloys and tungsten are more difficult. Defect can arise when the material does not flow properly in the die. For example, insufficient material may cause wet buckling, producing lapse. Excess material may cause internal cracks. Controlling temperatures and die design is crucial to avoid defects. Good die designs ensure proper metal flow. Draft angles must be provided to release the part, and flash dimensions must be controlled to avoid excessive forces and die wear. Dies must withstand high temperature, loading and wear, so tool steels with alloying elements are used. Lubrication also plays an important role in reducing friction and improving material flow. Dies are produced using a combination of machining, casting, and EDM. Failures occur due to wear, thermal cycling, or improper operations. Proper design and maintenance extend die life significantly. Forging machine includes hydraulic and mechanical presses, screw presses, and hammer. Each has different speed and force characteristics, making them suitable for different production volumes and part geometries. Although forging requires expensive dies, the cost per part decreases significantly as production quantity increases. For low quantities, casting may be more economical, but for high volume production, forging is usually the best choice. This case study shows a step pin formed through multiple cold forging steps, followed by piercing to form the bone. The process is fully automated with a high production rate. In conclusion, forging is a versatile and highly reliable process for producing strong and durable components. With proper die design, material selection, and equipment, forging provides significant performance and economic advantages. The material for this presentation were fully adapted from Chapter 14 of the Kalpakjian and Smith manufacturing process for engineering materials. And that is all of my presentation. Thank you for watching. Om Santi 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 Om.